Hello, Pythonists. I hope you are enjoying this PyCon 2019. As it is written on the slide, today we are going to talk about quantum physics in Python. First, let me introduce ourselves. Q squared, QSQRD, Q branch, just call it whatever you want. We just created this team 7 months ago to play with the computer and natural science. Therefore, this time we plan to make a session together. My name is Choi Hyun-soo, and I'm currently in high school's 3rd grade, preparing for SAT. And these days, I'm almost in love with my ThinkPad T480, and that's all about me.
And my name is Kim Hyun-sung, or you can call me Richard. I am a normal college student who are majoring in pre-science in University of Washington. This section is for the people who are interested in quantum computer and its algorithm in Python. If you have studied quantum computing before, this might be boring, but we will try to make this fun. We will explain the basic concepts of a quantum computer, and afterwards, we will take a look at some algorithms and how we can do all this in Python. I want to start this section with a question. What makes a quantum computer quantum? Or, in other words, what makes a quantum computer different from a classical computer? Well, while a classical computer stores information by using bits, a quantum computer uses a quantum bit, so-called a qubit. When classical bit has 2 types of information, which is 0 and 1, qubit has 0, 1, and its unique state, which is called a superposition state. This state is neither 0 or 1, but it contains the possibility of being either of them. This state does not collapse until it is measured, but when it is, the state will change to 1 or 0, depending on the state of the superposition. There is a way to take a look at one qubit in a geometric way, which is by using a Bloch sphere, which is usually used to take a look at one independent qubit. As shown from the picture here, the superposition state of a qubit is pictured as a vector in a space, which in this picture is notated as vector psi. The positive z-axis represents state 0, the negative z-axis represents state 1. The angle theta represents the possibility of outcome, and the angle phi represents the phase angle. Before we move into the next feature of a qubit, we want to go over some mathematical notation. In this section, we will be using what's so-called a bracket notation, where a ket indicates a vector. In quantum computing, the ket vector shows the possible state that can occur after measurement. Also, when it comes to more than one qubit, we use a tensor multiplication to bond the states. As you can see from the example, 2 qubits connect each other by tensor multiplication, and now there are 4 possible states. Also, we can translate the possible state from binary to 10-digit number because when there are a lot of qubits, the equation will be too long if you write all those possibilities in binary numbers. Now, another fascinating feature of a qubit is entanglement. When a set of qubits are entangled, they become one system. This is so weird that even Einstein called this spooky action at a distance. To understand this concept, we need to know a simple rule of physics, which is called law of conservation of energy. This law in physics explains that the total energy of an isolated system remains the same. As the entangled qubits act like a one system, this law of conservation of energy can be applied to the entangled qubits, which means if the energy of one of the entangled qubits change, it will affect other qubits that are entangled with that qubit. Now, using these features of a qubit, we can build a quantum circuits where we use a quantum logic gate that changes the state of the qubit, which you can imagine that the gate spins the state vector in the Bloch sphere. The first gate, so-called Hadamard gate, spins the state vector 90 degrees along the y-axis. This gate is most commonly used because if you apply an Hadamard gate to a qubit that has a possibility of being 0 or 1, 100%, the gate changes the qubit to a 50-50 chance. The X gate is used as a NOT gate, which spins the state vector 180 degrees along the x-axis. The third gate, which is called a CNOT gate, is a special one, as it applies changes to not 1, but 2 qubits. There is a controlled bit, and if the other bit is 1, it applies an X gate to the controlled bit. As the CNOT gate is applied to 2 qubits, it also have the effect on making those qubits entangled. Now, there are more kind of gates where you can find in a platform called the IBM Q Experience, a platform to build a quantum circuit. And actually, there are other platforms for this feature, but we decided to use IBM Q Experience. Using this, we can have a set of qubits, which in this case, there are 1. Note that as there are no gates applied to the qubit, the simulation of outcome shows 0 all the time. If we add the Hadamard gate to this qubit, the state of the qubit changes to superposition state. Note that the simulation of outcome changed from the last slide. This slide shows that the outcome to be 0 or 1 has same possibilities. This circuit uses a Hadamard, NOT, and a CNOT gate. Note that even though Hadamard gate is not applied to the second qubit, the outcome shows that the second qubit also changes. This shows that these 2 qubits are entangled, as the state of the first qubit affects the second qubit. And you can also compose a more complicated circuit in IBM Q Experience and execute it in a real quantum computer in IBM and get a result. So we took a look at the features of a qubit and how it is shown in a quantum circuit. Then, how do we write this in Python?
Let's see, seems it's my turn. Well, this physics mania has explained about quantum computing's theoretical basis perfectly. That's good, brilliant. However, we are developers. We need toolkits and playgrounds, or sandbox in other words. So I don't know, it can be a surprise or something, but we found so many libraries for quantum computing for various platforms. And of course, there are SDKs for Python as well. Also, they are one of the best runners in this field. They say great science is built on the shoulders of giants, and Cave Johnson, the founder of Aperture Science, said, we do all our science from scratch, no handholding. Whatsoever, SDK is something like those giants. They always help us so that we don't have to reinvent the wheel. All right then, let's take a look at them. And before I talk about the various species of SDKs, I want to make it clear about the mechanism of general quantum SDKs, and this is it. As you see here, you can first materialize your own circuit idea with the Python code. And when you run it, Qiskit will compile your code. To be more specific, it's your circuit in your code, since Qiskit is not a Python interpreter. This will just compile our circuit. Anyway, Qiskit will send the circuit data packed with JSON to the correct environment. And here's the thing. You can choose the simulator or the real device, I mean the quantum computer. You will need a simulator while you are debugging and developing new codes. So Qiskit of the great IBM. Actually, this is our favorite main library. As we tried plenty of libraries, seems like this is the most stable one with Microsoft's QSharp. However, since we are using Python, we can throw away that QSharp. And for now, I think Qiskit has the most friendly interface and documentations. But just don't forget, since these field structures are actively updating, so sometimes even Qiskit is not stable enough compared to many other open source libraries. This is a natural thing because most quantum libraries of these days are for scientific experiments and not for commercial use. Not for commercial use. I'm saying this twice since this is important. And Project Q is another great library for QC. There are many great things about Project Q, like this is made from ETA Jury from Switzerland. Anyway, their code is far more intuitive. You'll know when you read its GitHub repository. While this is having a better readability, Project Q can still use the IBM's backend. I mean, the IBM's quantum computer. There are many other frameworks for different languages beside this, but that's another story. And to make a quantum circuit, we need some HDL, hardware description language for it. One of them is Open Quantum Assembly Language, OpenQASM in short. It's literally something like a classical CPU's assembly language, based on many things. And for today, I'm gonna use Qiskit for a few basic examples. And its method will be Python 3. Thank you for your patience. Finally, we are showing you something PyConish. So to get started, we should install and import Qiskit in Python, of course. I would recommend using PIP inside Conda environment, but just pure Python and PIP will do the same. When you install Qiskit, you're all set. Just import everything from Qiskit. Well, sometimes importing parts of them is a lot more efficient, so just choose wisely. In addition, you can use a Jupyter Notebook while you are using Conda. Google Colab is not a bad option too. Just install Qiskit on it. After you imported all elements you need, you have to create some registers and a circuit. Quantum circuit is made with two elements. One is a quantum register and the other is a classical register. Most of the operations will be done in that quantum register, and the classical register will be some kind of slot for storing results of qubits. And when you combine them, you can create a proper quantum circuit. In this slide, the 3 lines of code on the left is equivalent to the circuit diagram on the right. Also, don't forget the number of both bits. Each register has 2 bits inside, since I gave them as a parameter. And this is what we are waiting for, adding some spice of a superposition, randomness in other words. If you remember Richard's explanation, we need a Hadamard gate for superposition. So let's apply h gate to the first qubit. Function h takes the index of qubit as a parameter. Okay, now we have one superpositioned qubit in our register. Furthermore, we can add some flavor of entanglement, which is one of the most beautiful things in quantum physics. With the second line of code, I just entangled the first and the second qubit together, using the first qubit as control bit, so we can expect that 2 qubits are sharing the same state. And since one of them is in superposition state, the result will be 0, 0 or 1, 1. And let's measure them all. Every qubit's measurement results will be stored to corresponding classical bit. Finally, we should run the circuit, select the backend simulator, and declare our job. Then we can run them by calling the function result, and the rest of them are easy, needless to say. Good. And if we have these frameworks, we have plenty of things to make and enjoy. So let's start with the easiest, basic one. God does not play dice, said Einstein, the physicist with some fuzzy hair. That was his answer to quantum physics. However, the quantum computer has released to programming field. Perhaps we will dare to say we have the dice now. Theoretically, quantum computer can guarantee us a perfect random number generator. This is just a little web app we made with Qiskit and the graphing library called Dash. Maybe some of you guys heard of it. This cute server script creates a few qubits and put them into the superposition state. So we have some qubits with an equal probability of 0 and 1. When we measure them all and convert those library results to decimal, we can get a complete random number created by a quantum computer. However, the problem remains. Since quantum computer has some tricky problem called quantum noise in their system, we can't achieve 100% accuracy. Since many people are working on this to solve it, time will solve such problems. And this is how it works. So I just converted its result to binary and then to decimal. And another thing we can do with the spooky computer is a game. Like old hackers of 20th centuries, we can hack and tinker with this new computing technology. On GitHub, there are such a lot of games made for quantum computer, and some of them is made by IBM. You can clone and enjoy any of those games enough to, so we also made one. Since there was a lot of simple games already, we decided to make a game which is worth enough for such a computer with astonishing specs. Our game had to require high specs, not just like these days classical computers. So what we made is a Minesweeper. Yeah, so as I remember, this is the first thing we made after we read the documentation of Qiskit. Also, as a developer of this little game, I guarantee you this is not really fun. The thing is, quantum computer can be used to various fields. Well, so this game's quality isn't very good, but it runs. It's a prototype, and it runs.
Okay, so forget about the Minesweeper or whatever you call it, because we have a bigger question ahead. Why do we have to use a quantum computer? Because we already have some amazing classical computers. And why do we even have to use a quantum computer? Well, the answer is because it's faster than a classical computer when it comes to certain fields. And one of the examples to prove this is an algorithm called Deutsch's algorithm. This algorithm, made by David Deutsch and Richard Joza in 1992, solves what's called a balance problem, which the goal is to figure whether the function is balanced or constant by only looking at an input and an output. When we use a classical computer to solve this problem, we need to initiate the function twice, which then will take more time. However, with Deutsch's algorithm, we only need to initiate once. How? Well, that's what we are going to find out now. First of all, we prepare 2 qubits. We set the first qubit at 0 and second at 1. Therefore, the possible state is only 0 and 1 for now. And then, we apply an Hadamard gate to both qubits. Note that the sign of some states are negative, which because the Hadamard gate was applied on a state 1 for the second qubit. Then, apply a unitary gate that just passes the same value for the first qubit, and value of a second qubit tensor plus the output of a function with the input of the value of a first qubit for the second qubit. After this procedure, the state vector looks like the first line in the slide. Now, if we have a constant function, the output of a function with different inputs will be the same. So, applying those rules, we can rewrite the equation, just like the slide shows. Also, if the function is balanced, different inputs result on opposite output. So we can also rewrite the state vector with applying those rules. Note that the equation of the state vector is different on the constant function and a balanced function. Later, this will make a difference in the output. Lastly, we apply a Hadamard gate and measure only on our first qubit, which then, if the function is constant, the result will only show 1, and when balanced, the result will only show 0. Now, this is a Deutsch's algorithm with a constant function designed in IBM QExperience. Note that the first algorithm has a function of fx equals to 0, and second has fx equals to 1, as the second qubit has an x gate. Also, the result shows 0 for the first qubit. This is also a Deutsch's algorithm where the function is balanced. The first circuit shows the function fx equals to not x, and the second circuit shows when fx equals to x. Note that the result has 1 most of the time. The reason for that 10% that you show in the graph, that you can see in the graph, is because of the quantum error, which is also called decoherence. So we just looked at Deutsch's algorithm, which proves that the quantum computer is faster than a classical computer in certain situations. However, just proving that quantum computer is somehow faster does not tell us everything. We have to ask, is quantum computer can do something useful? Well, the answer is no, but it has potential to be. For example, we have a Grover's algorithm, which is a searching algorithm that can process much faster than a classical computer does. We can also use this advantage of searching feature that quantum computer has, which is on Shor's algorithm. With this algorithm, we can search for A and B with n given when n equals A times B. So the big question is, how do we do it? Well, to explain that, we need something very important, something very, very special. We need a cat. No, we need an example. We need a good example. So what we're going to do is set up a number n, which will be, of course, complicated and something really big. So let's say n equals 15. That makes our goal to find two numbers that makes 15 when they are multiplied. What we are going to do first is to guess any number which the common divisor between g and n is 1. So let's say it's 7. So we're setting g as 7. And before we go to our next step, we need to go over some maths. One marvelous thing is there is a natural number that when used as a power of g, which in this example is 7, has a remainder of 1 when divided by n, which is 15 in this case. And with this information, we can do something very interesting. Just like what the second line in the slide is showing, we can move the remainder plus 1 from the right-hand side to the left-hand side. And then we are able to factor to two parts, which means we can find out a and b by finding the greatest common divisor of factorized number and the number n. So all we need to find is a power p. So let's ask our cat. The way it goes is quite simple. First, you select another random number. So it's 2. So we take the number g, which in this case is 7, and take a power by 2, which will be 49. And then we divide it by the number n, 15 in this example, and get the remainder, which is 4. But it's not 1. So we would need another random number. Let's see, never mind. So this is one way to find the power by using classical computer. But, well, the thing is, it takes too much time. We don't have time to repeat all this. And that's why we need a quantum circuit. In the circuit, we need to separate the bunch of qubits to two sets, upper and lower. The upper set will be applied with the Hadamard gate, so that those qubits would be in a 50-50 chance of being 0 or 1. And then we need a quantum cat. And a superposition, of course. We prepare an upper set of qubits, which are in superposition, and then we connect those with the lower set. We set the connection as the lower set represents the n to the power of the upper set. Therefore, as we can see from the slide, all the possibility of output shows that the lower set has 7 power to the upper set. And then we divide the lower set by n, which is 15, and change the possible outcome of the lower set from g power to the upper set to the remainders. So note that the lower set changes from the powered numbers to the remainders. Now, we might think that we are done here, but if we measure here, what we get is just one of those possibilities, and that has no difference with a classical circuit. So to get closer to the answer, we need to go some more math. Now, you might have noticed from the last slide, but we already found a power that has a remainder 1, which is 4. Now, let's assume that we do not know this. We divided 7 to the power of 2 by 15 and got 4 as a remainder. We keep increasing the power and found that actually the remainder of 7 power of 6 divided by 15 also has a remainder of 4, and 7 power by 10, 14, 18, and so on. This shows that the same amount of remainders repeat in the period of 4, which actually is a number which, when used as a power, has a remainder of 1. So to find out the right number, we just need to find the period that repeats. And the quantum circuit uses a fantastic way to isolate the period, and the way is to measure. If we measure the lower set, then the lower set will give us one of the remainders, which in this case, 3, randomly chosen. We haven't measured the upper set yet, so all the other power that has different remainders disappear. Note that the remaining upper set increases in a rate of 4, which when used as a power of the remainder is 1. So we can think that we can just measure and get our result here, but if we do so, just like before, we would just get a random number from the possible states. So that means we're not done yet. We want the result to be exactly the period. And to do that, we are going to use so-called the quantum Fourier transformation. The quantum Fourier transformation converts a state to a wave. And in this case, all the possible states convert to a wave and intercept each other. As a result, only 1 over the period is left. So when we measure after applying the quantum Fourier transformation, we would get 1 over 4, which then we would be able to flip it and get the right period. So let's check. We got 4 as our period. So if we calculate the common divisor between 15 and 7 power to the 4 divided by 2 plus 1, which then is between 15 and 50, we get 5. And we do the same with another factor, we get 3, where if multiplied, it becomes 15, the number n. So we are done here. But there are also other ways to find the period. And it is to use inverse quantum Fourier transformation instead of the quantum Fourier transformation. This algorithm uses a phase estimation to assume a phase of an eigenvalue of an eigenvector in a unitary gate which applied on a lower resistor, which then we are able to find the period using the phase value. This quantum circuit is easier to build using gates supported by IBM Q Experience. However, it requires more complicated math. This picture in the slide shows how the quantum state developed to get the phase value. Note that the Fourier version gives us 1 over the period, while the inverse Fourier version gives us the phase value. And this is the quantum circuit of a Shor's algorithm using an inverse Fourier transformation designed in IBM Q Experience. Note that we are using CRZ gate most of the time, which is called a controlled Z gate. This gate applies to a certain amount of rotation to the controlled qubit when the other qubit is 1. For more information about this circuit, please visit the IBM Q Experience site. So then, we just looked at some algorithms, and the question is, how would we do this in Python?
Okay, then I'll explain how this can be done in our laptop. To use quantum algorithms, there are 2 options. First, you can make a bottom-up approach with each qubits and gates, reading the documentation of existing algorithms. Second, you can make a top-down approach using the built-in functions. Well, actually, I don't think we have to reinvent the wheel. Qiskit has 3 main parts, while Qiskit Terra is for basic quantum operations, and Air is for simulation. Qiskit Aqua is our toy box filled with useful algorithms. You can just call them as functions and use them. So remember the algorithms Richard just explained. They are the key technology of quantum computing. Like in classical computer, algorithm makes computer to do something useful, of course. Without them, computer is just a collection of light bulbs. Therefore, it's obvious that we should use quantum algorithms. Shor, Grover, Deutsch-Josser, BB84, there are so many algorithms you can use. And for the first example, I want to use the Shor algorithm, which can factorize large numbers and theoretically break RSA. And also, we may find new prime numbers when we have enough computing power to factorize them. And this is the basic example of a Shor algorithm using Qiskit Aqua. I just skipped the previous input statements, but you'll need them easily from the IBM's documentation. In this example, we are factoring 15 as n. As you see, we can get our results easily. It's even easier than running Apache Server or something. And this is the OpenQASM code describing the Shor algorithm circuit. And then why don't we just hack into anything and take over the world? Yeah, but no, but yeah, that's simple. We don't have enough qubits and performance. And when we try to use a simulator, we realize that simulator is not a real quantum computer, which means there's a limit of speed, results, etc. Also, there's a tricky problem called quantum noise. As you can see from its name, the phenomenon makes qubits to lose their accuracy. So it's incomplete technology for now. However, incomplete is not equal to useless. This is rather a big threat. Well, there are a few problems, but many people are still working on it. For instance, Qiskit recently included a new element called Ignis, which mitigates the quantum noise. And talking about the limit of a simulator, actually there is no problem with the limit on the simulator. We can just test the small cases from simulator and use the real device when it gets massive. Anyway, now we know that RSA can be broken someday, so what should we do? Luckily, we have the QKD. If we can break the existing cryptography with the quantum computer, why don't we try making the better system with it? So what is the QKD? Another public key crypto system like RSA? Well, it's similar to RSA in some part, but a lot different. This is important, so please concentrate. While RSA can encrypt and decrypt the specific data, QKD can't. The data will be random, and there's nothing user can do. What QKD can do is literally distributing the same data for two users. We don't know what data Alice and Bob will get, but one thing is clear: a pair of data will be same. I don't think QKD is really popular for everybody, but there are some interesting experiments using QKD. For example, Japan made the Tokyo QKD network to make a quantum encrypted communication, and China succeeded in making encrypted quantum communication with their satellite. Then you might wonder how this thing is even working. The answer is reverse the polarity of the photon. Well, this set of pictures explains it better than me. Just play with the polarity. Anyway, to do this, we are using the algorithm called the BB84 protocol. This is developed by Charles Bennett and Gilles Bressard in 1984. Well, it's actually easy. Rotator just rotates the photon, or you can say quantum. We don't really need to know how. That can be done. What we need to know is what can we do with that. So it's going to get long. So I will simply explain the protocol. Let's think Alice and Bob is going to share the secret key and make some secret communication with that. Well, we don't know what encryption protocol they will use, and I don't care. The thing is, how can we distribute the same key for Alice and Bob? First, Alice creates the sequence of random qubits. This will be the basis of key. Then Alice rotates each of those qubits all randomly. Randomly means that Alice will choose the random filter to change the polarity of each qubit. Then Alice will send a polarized set of qubits, to Bob. And Bob will do the same to that set of qubits. He will pick random filters and measure qubits with them. And Alice and Bob shares their set of filters. That's called a public discussion. Finally, they compare their filters with each other's one in a public channel. When they see the same filter in the same index of a filter list, they decide to use the qubit on that index. Mostly about 50% of them will be selected. And now Alice and Bob will share the same selected and measured qubit. Now they can use AES or something to use that key and make their secret conversation. I know this is rather complicated, and because this explanation is quite simplified, it's not 100% accurate. So, and also there are a few more great features like detecting the eavesdropper, crackers. But using this for real encryption is never easy. RSA requires only some classical computers with minimal specs. Even Raspberry Pi can do it easily. However, QKD isn't. This requires the giant QKD network which can make communication with the photons, and I think you can feel how expensive they are. So yeah, we want this. Needless to say, it would be absolutely fantastic if we can build this. But just think of it, it's actually impossible. Build the worldwide QKD network and launch the satellite? Well, at least I can't, not yet. I'm not some kind of a hardware engineering expert. Okay, then what should we do? For instance, what if we can even simulate them? Everything of a BB85 protocol. Change the polarity of photons, sending them, measuring them, everything. Luckily, I could find some examples written in Python and Qiskit. I added a link of that Jupyter notebook to my repository, but seems like that's gone about a month ago. No problem, I cloned them even before that. These are the examples of a basic QKD code written with Qiskit. And this, the problem was that example code was written for single script. Single code was just sharing same variables, not a communication. Basically, there was no sender and a receiver. Well, that was a great code. However, I wanted a real communication with the quantum key distribution. In my opinion, it's not real difficult to divide a single code to server-client type. Then only one problem remains, sending the photon. Even if we have Qiskit, we have to send those simulated qubits to other clients. And here comes a crazy idea. We don't have the radio communication system, but what if we can pickle the qubit with Python? Qubit and the entire quantum circuit is also an object in Qiskit. Why not just serialize them all to text file? Okay, somebody may say, Pickle has so many vulnerabilities. But the thing is that I don't care. What I care is simulating the QKD, BB84. When I was developing this, nothing else was in my mind. And you know, what's the best communication method for this kind of a raw text data in Python? It's the socket module. All I had to do was packing this data with the Pickle in Alex's computer, write them on file, and send it to Bob's computer. Well, it wasn't always easy like that. While clients are sharing, sending, receiving the qubits, I met tons of errors. And since I didn't use a socket in Python very much, debugging them was not that easy. However, ignore the process. We succeeded. This is working. This thing is really cute. And actually, we made the JavaScript client as well. Just forget it. And there's one more thing, which is called quantum annealing. We recently started this, and our theorem manager will explain about this concept. Seems like time's running out. Just, yeah.
Yes, so what we wanted is to explain about the quantum annealing, which is different from quantum gate, but apparently we have only 40 seconds left, so we kind of have to wrap up right now. For our last words, we don't think that we can actually make money with this right now. The actual reason why we are doing this is because it's fun, and something new is always entertaining. So thank you for coming to our session, and this was Richard Kim and Samuel Choi. Thank you.